All right, so here we are at the end of Unit 7. So this is going to be a little bit of a longer video because we are doing an overview of this unit. So by this point, you should have gone through all of the individual lessons. So this is just to recap. I want to say, I'm going to put in the description below the time stamp for each section, not each problem. So 7.1, 7.2, 3, and 4, and so on. So you can just go to that point in the video wherever you need to. Okay, so looking at section 1, starting with our two vectors equivalent. So two vectors are going to be equivalent if their component forms are the same. So with our S and P to Q, we have to come from S to O, meaning 0 minus 2. So 0 minus 2, and then negative 1 minus 1, which would give us, and this is our S, which would give us negative 2 comma negative 2. And then for P to Q, it is very important that we understand that our x2 and x or y2 is the Q wherever we're ending. That is very important here. So we have negative 1 minus 1, and then 2 minus 4. So we get negative 2, negative 2. We see that the two component forms are the same, so that is enough to prove that they are equivalent. All right. So keeping that in mind, knowing that we'd have x2 minus x1, y2 minus y1, looking at the second scenario. So if vector u, or rs, is this component form, negative 2 comma 5, and then we're given the location of r, determine the location of s. Where, while looking at this, s is our x2, y2, looking at the name of the vector. So knowing the component form and the initial point, I can say that negative 2 comma 5 must equal x2 minus negative 6, and then y2 minus negative 5. All right, so we get x, I can say, oh, x plus 6 must equal negative 2 over here, and then y2 plus 5 must equal 5. Okay, so with some quick manipulation, we see that x2 is negative 8 and that y2 is 0. So the coordinate of S is negative 8 comma 0. Slide over there, we go. Okay, and going from there, looking at magnitude. So magnitude, we related it to the very well-known Pythagorean theorem. So we take the two components, horizontal, vertical, square them, add them, and then square root. We use this notation, our bar, that well, it looks like absolute value. So we would get the square root of negative 9 squared plus 3 squared. Knowing that negative 9 squared is positive, so we get positive 81 plus 9. So we can say the magnitude of V is the square root of 90. And we do not give an approximation. We leave it as the square root of 90. Moving on. So vector operations. The whole idea with vector operations is that x's with x's, y's with y's. So if I am wanting to add u with v, I add the x component, which is I, and I add the j component, which is, or sorry, the y component, which is j. So if I want to do u plus v, that's saying, okay, that is negative 7 plus 2, and then 1 plus 5, all right, but we have i's and j's here, but they want the component form, so we're good. Let's see, that would be negative 5 comma 6. If I wanted to do the linear combination form, it would be negative 5i plus 6j, just so we know how we would do that. So looking at negative 3v plus 4w, so that would be, just going through this real quick, negative 3v, which is multiplying both components by negative 3. Okay, and then they want us to add 4 times w, which is just negative 3j. So that would give us negative 6i minus 15j plus, we'll say 0i, since there's not an I component there, minus 12j. All right, and then that would mean for us, okay, then our result in component form is negative 6 and then negative 27. All right, so then looking at the next one, 2w minus u, so 2w, w is negative 3j again, minus u, which is negative 7i plus j. So that'd be negative 6j minus negative 7i plus j, all right? So 0i minus negative 7, that turns to positive 7i. Negative 6 minus j, be negative 6 minus 1, so be negative 7j, which as a component form be 7 comma negative 7. All right, moving on, next one. So we have negative 5 multiplied by u. Now you might get this confused with the dot product that we'll look at eventually, but we're multiplying by a scalar, by a number, not by a vector. So this is just what we did up here, multiplying u by negative 5. So u is again negative 7i plus j, which would give us positive 35i minus 5j, so we get 35 comma negative 5. Okay, so not that bad so far. So within section 2, looking at unit vectors and direction angles. So find a unit vector in the direction of the given vector, v equals negative I plus 3j. So in this, we have a formula, and it's just a matter of knowing how to use the formula. And doing that, we divide the vector that's given to us by its magnitude. So we need to find the magnitude of this vector. So that would be negative 1 squared plus 3 squared. So that'd be 9 and 1, which is the square root of 10. So we take the vector and divide it by square root of 10. So leaving it in the linear combination form, the I and the j, it would be negative 1 over root 10 I plus 3 over root 10 j. And you could also write it as, since we're not told how to write it, we could write it as negative 1 over root 10 comma 3 over root 10, and this is component form. So magnitude, divide the vector by the magnitude. So doing this again for negative 2, negative 7, so we need the magnitude of the vector. That would be the square root of negative 2 squared plus negative 7 squared. So that would be 49 plus 4, which is 53. So we have the unit vector. I should say up here, this is the unit vector. And down here we would have the unit for u. Okay, and that would be, let's see, negative 2 over root 53, comma, negative 7 over root 53. All right, and with that, so finding unit vector, now find the direction angle. So there are two approaches we could take here. We could take the approach of knowing that vectors have, magnitude times cosine of theta, magnitude times sine of theta. We could take that knowledge and set negative 3 equal to this. So this would require of us to find the magnitude, and we later on just said, oh well, if I want to find the direction angle, it's going to be equal to the arc cosine of, well, the x component, so I'll say the x component of the vertex divided by the magnitude of the vertex. If I did arc sine, it would be the y component over the magnitude. So if the magnitude of this vector, so we'll call it vector v, its magnitude is negative 3 squared plus negative 5 squared, it's 25 plus 9, which is 34. So we could continue and say, oh, well, then the direction angle is the arc cosine of, see, the x component is negative 3 over the square root of 34. All right, so that's one approach. That's how you first were shown how to find the direction angle. Another approach that you just recently have heard of through our discussion is that I could, rather than finding the magnitude, let's say I'm in the problem and I already already had the magnitude, well then why not just do this? But if I just had a problem, not started it yet, nothing is found, I just had the vector, and I want the direction angle, well I could do this instead. I could do the arctangent of the y component of the vertex divided by the x component. Doing that, I would not need the magnitude. So it would look like the arctangent of -5 over -3. And let's see what we get here. So if I type in, let's do this right side first. Let's say I'm in degree, perfect, arc cosine of -3 divided by square root of 34. We get approximately 120.9638 degrees. Okay, now knowing that the vector is in quadrant 3, this is in quadrant 2, so I'm going to have to subtract from 360. 120.9638. Again, subtracting from 360 because that will give us quadrant 3. All right. So we get a direction angle of 239.0362 degrees. Now, how does it change when I use arctangent? So say I want to do, instead of doing all of the arc cosine, I want to just do arctangent of -5 divided by -3. We get 59.0362. This is in quadrant 1. So to get quadrant 3 with this angle, I would take 180 and add this. So this, knowing whether to use 180 or 360, that just takes some thinking, some logic there to know what quadrant would take me where. But if I do 180 and then we add this value, oh, we get 239.0362. All right. So neither of these will give us the angle straight away. Both will require some one last step, whether it's 360 or 180. All right, moving on. Still in topic 2. So now write the component form of the vector when given its magnitude and direction angle. So some of these can be really quick. For example, we have magnitude, we have direction angle. Perfect, because I can use my magnitude cosine, magnitude sine. So it is 31 cosine of 46 and 31 sine of 46. To give us a visual of what's going on, so we're in with our direction angle, we're in the first quadrant. Okay, so use the color. So we have a 46-degree angle. And the length of the vector, the magnitude is 31. So we've learned that we have the components. We have the horizontal component and we have the vertical component. That's what we were doing here. All right, moving on to the next. Find the component form of vector u with a magnitude of 14, but in the direction of w. So we're not given a direction angle. So we could find the direction angle with w, or as an alternate, we could take and do this. Find the magnitude of u, oh, we have that, okay, and then multiply it by the unit vector in this direction. So if I can find the unit vector of w, then I would simply take my magnitude and multiply that vector. Okay, so the magnitude, I need to find the unit vector, I need the magnitude of w. That would be, let's see, the square root of -2 squared plus 9 squared, that's 81 and 4, so that's the square root of 85, which would give us a unit vector of -2 over root 85, comma 9 over root 85, perfect. Okay, so now to get this vertex u, I take my magnitude and multiply by this unit vector. Okay, and that would give us negative 28 over root 85. And then, see, 14 times 9, I believe this is going to be 128, 126. Hey, 126. Okay, and there we go. This is vector u. And if you found the direction angle, if you had the direction angle, you would get a direction angle of approximately 102.5289. So if you had that and you did, let's say, 14 cosine of that angle, all right, you get this. Watch what happens when I take negative 28 and divide it by root 85. We get the same exact thing. And then if you did 114 sine of that angle, it's going to equal this as well. All right, so that's how we do it if we had the magnitude and the vector we wish to go in. That's a little time-consuming problem there. But moving on to something that's a lot easier. So baseball is hit off the ground, hit off a bat, 38-degree angle. So we have our direction angle with an initial speed of 107. So there's our magnitude. Find the component form. Well, to give us a visual, 38-degree angle. It's hits the bat at 107 miles per hour. So components, just 107 cosine of 38, 107 sine of 38, and finished. So this is the x component of the velocity, of the initial velocity, and this is the y component of the initial velocity. Just knowing what those two numbers represent. And then, kind of similar idea, a box is being pushed up a 10-degree incline. So again, here's our direction angle at a force of 29 newtons. So there's our magnitude. My goodness. So we would have magnitude cosine of 10 degrees, comma, magnitude sine of 10 degrees. So with this problem, I say disregard friction. We're disregarding, a lot of things like the force of gravity and the normal force, and so this is just the components of the pushing force, the force that's applied to the box. All right. So let's see. Now we are in section 3. So section 3 is where we discussed the dot product and the angle between vectors. Up to this point, it's been the direction angle, the angle from the x-axis. This is the angle between vectors. So perform the dot product on the following vectors, and if it's 0, no, that's orthogonal. Okay. So let's say that we have our 3 vectors. So let's go with this. So dot product of u and v. So -1, 9, dot product with 6 and -2. Dot product straightforward. Multiply the x's and multiply the y's, the y components. So that would give us -6 plus -18, which gives us, I believe, -24. That's the dot product. If it's not 0, it doesn't really tell us much, only if it's 0. Now the next. So we have the dot product, so we have w, dot product of this sum. So I could do the dot product of w and u and add it to the dot product of w and v, or I could add u and v together first and then perform the dot product. And that's what I'm going to do. I'm going to add u and v together. So when I add u and v together, I get this vector. So u, so -1 and 6, that's +5. 9 and -2, that's +7. That is this sum. So now we're going to perform the dot product with w, which is 3, 5. Okay, so that is 3 times 5 plus 5 times 7 So that's 15, 15 and 35, that's a dot product of 50. There you go. So there are multiple approaches to that, but they all come down to 50. So calculating the angle between the vectors. So this is within this section because how we find the angle between vectors, we need to find the dot product. So find the dot product, find the magnitudes, and take all of your numbers and place them in. So it would look like this. So we're finding the magnitude of u, 25 and 4, so 29. Find the magnitude of v. So 25 and 9, that is 34. Okay. Now we need the dot product of those two. So that would be, let's see, 5 times negative 3, and then 2 times 5, negative 15 and 10, so negative 5. And now our angle between the vectors is the arc cosine. Yes, it's always cosine for angle between vectors. Arc cosine of the dot product, which is negative 5, divided by the two magnitudes being multiplied. So we should know this formula, dot product and then the magnitudes of each. So typing this in, let's see what we get. So we get the arc cosine, let's say alpha y equals, get this little fraction symbol for us, negative 5, square root of 34, and square root of 29, gives us an angle of approximately 99.1623 degrees. And when you get an angle measure here, it is the angle between them. There's no other alterations needed that we needed to do for direction angles. This is the angle between them. Okay, so we have a vector that's in quadrant 1, a vector that is in quadrant, let's see, maybe quadrant 2. I should say, as I'm saying that, I'm assuming that these vectors are starting at the origin, which we typically assume. Moving on, that's dot product and angle between vectors, and ending here with the application of vectors. So pay attention when you're doing these problems to opposing horizontal and vertical components. But if you do this correctly, you should not have to worry about that. So we have a force of 50 pounds acts on an object of 45 degrees, 75 pound force acts on the object at negative 30 degrees. So we have this box, and we have from 0 degrees, we have at a 45 degree angle, a 50 pound force. And then with a negative 30 degree angle, we have a 75 pound force. Notice I'm not even worrying about drawing this to scale, because scale really does not matter. Okay, so we want the direction, meaning direction angle, and the magnitude of the resultant force. Okay, so we want to find the components of each and then combine them. So I'm going to use blue for the 50 pound force. So we have our vertical component, which would be 50 sine of 45. And we have our horizontal component, which is 50 cosine of 45. All right. Next, we have our 75 pound force. So we have the vertical component. If you, I'll come back to that. So we have 75 sine of negative 30. And then we have 75 cosine of negative 30. Okay. We add the vertical components, we add the horizontal components. So it would look like, let's see, okay, I'm just gonna stack these up. 50 cosine of 45, 75 cosine of negative 30. Okay, and then we would have 50 sine of 45, and then 75 sine of negative 30. All right. If I included the negative on the angle, because the negative indicates that it's going in the opposite direction of the 45. If I include the negative there, we can just add our components. Whereas, if I treated this as a positive 30 degrees, I would need to recognize, and so would you, that the vertical component is going in the opposite direction as the other, so I would have to subtract them. But again, if I include the negative, it's done for me. So we're going to take each of these and we're going to add them together. So we're going to add the vertical and the horizontal. And doing the calculations for us already, we get the components of 100.3072 and then negative 2.1446. Again, I just added my horizontal and my vertical, added them together on our calculator. And that is not it. We have to continue and find the magnitude. So the magnitude we can do rather easily, just with decimals. We have our resultant force, we have the magnitude of it, which is, square root of the two components squared. Okay, and the calculation with that, we get a magnitude of approximately 100.3302, and that would be pounds of force. Now we desire the direction. So we already have the magnitude. So back in section, I believe it's section 2, I could do arc cosine of the x component over the magnitude. I can do that since I already have the magnitude. But we can also here go ahead and do the arc tangent. That's what I'm going to use. I'm going to use the arc tangent of the y component divided by the x component. Okay, and when we do this, let's see what we get. So arc tangent of negative 2.1446, and dividing that by 100.3027 gives us negative 1.2248. All right, and with that, let's see. Let's say if I did the arc cosine. So arc cosine of the horizontal component, dividing that by the magnitude, gives us positive 1.268. So it's interesting that we're getting, from one we're getting a negative angle measure, and for the other we're getting a positive angle measure. So thinking here, thinking of what quadrant we would be in, our component says go right and then down, that those are the components of our resultant. So if you think of quadrants, that would take us to, the fourth quadrant. So our answer would be negative 1.2248 degrees. So we are in quadrant 4. So we have a negative angle measure, negative 1.2248 degrees. And really, if I were to say 360 and I want to subtract, we get this. This would be another way of doing that. I'm wondering, okay. So I'm sitting here wondering why we're getting a slight variation. Nobody's have 2248 and 2268, and it comes down to when we had the magnitude, we rounded, we cut that off, and there we're going to get some error. Okay, but you have to recognize that we are in quadrant 4, so it's either I take the cosine angle that I get and subtract from 360, or using the arc tangent, recognize that the negative gives us in the right spot. So a little bit of thought there at the end, looking at the last. Okay. So a force of 12 newtons is pulling a box at 120 degrees. The second force, okay. So let's work with this one. Move our box. I want to say this, back to this problem up top. When you're finding the direction angle, if you use, whether you use the arctangent of the components or you use the arc cosine of the component in magnitude, you have to check where your angle is and whether that angle matches up with your vector. My vector, the force vector, is in quadrant 4, having positive and negative. So I have to make sure that my angle that I get, the direction angle, is in that quadrant as well. I have to do that. So looking at this last problem. So we have a force, one force, here's our 0 degrees, one force pulling at 120 degrees. And then at a force 12 newtons. And then another force pulling at 71 degrees. This is 75 degrees actually. At a force of 21 newtons. Okay, components and then add them together. Let's do this. So of our 12 newtons we have, let's see, 12 sine of 120. And then 12 cosine of 120. All right. We have our 21 sine of 75 and 21 cosine of 75. Our x components go in opposite directions, but in this case, I'm not going to subtract them. I do not have to subtract them. The reason being is because cosine of 120 is going to give us a negative. Cosine of 120 is a negative value, so that's where we will get the subtraction. And meaning, I can just add them. I said this. If you do this correctly, you will just have to add your components. So 12 cosine of 120 plus 21 cosine of 75. All right, 12 sine of 120 and 21 sine of 75. You add them together, you get the components of negative 0.5648 and then 30.6767. So that's the component form for the resultant force. We need the magnitude. So working through the magnitude you should get, I'm not going to do this here, I'll just tell you what you should get. The magnitude should be 30.6819 newtons. And then you should get an angle measure of 91.0548. Now I found that using the arc cosine. So I found out using arc cosine. So I'm going to test this out with the arctangent. So let's clear this here. So arctangent of the y component divided by the x component. Okay. We get negative 88. Okay, we get negative 88.94522. So knowing that that is in the fourth quadrant, but our vector, looking at it, our vector's in the second quadrant. So if I do 180 subtract, actually, or just 180 subtract this, but notice I'm just logically reasoning through this. So there we go. We get our 91.045. Using arctangent here, it did not give us an angle in the correct quadrant. I had to recognize that and work with finding. So whether you use arctangent or whether you use arc cosine, you're gonna have to, again, ask yourself, is the angle in the right quadrant? So I hope you did well whenever you did this on your own. Maybe you did not do it on your own, you needed some help with it, that's fine. But I wish you the best of luck as you continue to prepare for this end of the unit assessment. Guys, I'll see you in the next unit. Again, good luck on this test.